Way cool.
In this experiment, we're going to implement convolutional decoding using the TIMS DSP module. Please open up your experiment manual to Chapter D2, Experiment 9, Figure 5. We'll be implementing the system with convolutional coding through a noisy baseband channel, decoding implemented by the DSP, and then bit error rate measurements. This will serve as a convenient way of demonstrating how the DSP fits into the scheme of things with TIMS modules. So, starting off on the left, we have a sequence generator which is being clocked at 2 kilobits per second, and it is sending data into the convolutional encoder module. Up here on the scope you can see we are triggering on the sync pulse of the sequence generator so that we have a stable and easy to view signal. We have a look at the data coming out. You can see that it is stable digital stream, repetitive, periodic, and we have selected a short sequence just for the purposes of keeping the display easy to view. So we have the digital data coming into the convolutional encoder, and coming out of the convolutional encoder we have the convoluted data, and as you can see it is operating at twice the bit rate of the data going in to the convolutional encoder. Take our probe, have a look at the output of the line code encoder. It is simply an NRZL version of the convoluted data. So it is level shifted, plus or minus 2 volts. Level signal. We then take our probe once again, and I'm moving quite quickly here just to demonstrate the signal flow of the system. If you refer to the experiment in the manual, all the steps are expressed there. Have a look at the input to the baseband filter. You can see that it is very noisy signal. We have added noise in the channel, and at the output of the baseband channel filter you can see now that we have some band limiting from filter number 3, you can see the band limiting effects on the line coded data with a little bit of noise. Currently the noise is set to a minimum level. Okay, this experiment is very similar to the other video where we did line coded data in a noisy baseband channel, except that in this case the data is convolved through the convolutional encoder instead of being simply line encoded. You have many options in the encoder, code 1, code 2, and all these features are discussed in the user manual, the advanced modules user manual. I won't go into them here. Okay, we have our noise, then that noise, the noisy signal goes into the decision maker, and we set up the decision point as we discussed in the other video, which I refer you to. It's from the manual D2, experiment 1. Coming out of the decision maker is the signal after it's been sampled and cleaned up. That signal is then passed through a line code decoder module and comes out as a TTL signal. Now at this point we have TTL clock at the receiver, TTL data at the receiver, and we have the clock at the receiver, and these signals are convolved data. Now they need to be put through the convolutional decoder, which is where the DSP comes into play. Now on the rack here you can see we have our single slot modules, but we've put the DSP module on a separate module down here on the table, and we've taken the leads from the line code decoder and taken them down to the DSP module. So what I'll do is I will show the DSP module now. Just down here on the table, you can see the DSP module connected via USB to the laptop, which is running the program. And you can see the format is very similar to a TIMS module. 4mm terminals in, analog to digital converters at the top, and digital inputs and digital outputs at the bottom, and some user interface devices which are program accessible on the right. So we've taken the signal out of the line code decoder, which is basically our recovered TTL signal. We input it into the digital inputs, and then we're running the program on the laptop, and the output is the deconvolved signals, which we'll have a look at in a minute. We're switching over to the laptop. There isn't much to see, but we're running Code Composer. You can see it's running, and when it runs, the program gives a little bit of information. So let's come back over to the scope. Have a look at the scope. Alright, set ourselves up in front of the scope again. Okay, so grabbing our scope probes, we'll look at the input. Okay, turn the voltage range down, that's the clock. We'll look at the data going in. Okay, and now you can see the signal here, the blue signal, is the data going into the convolutional decoder, which is implemented on the TIMS DSP card, and the orange signal is the data coming out of the convolutional decoder. So that ought to be the original, I'll just back a bit. That ought to be the original signal coming out of the sequence generator, but way back here. So let's have a look at that. We'll take this out and we'll view the original signal back here, and we will change the time base, and if you look, you can see the original signal, at the top, with the recovered signal at the bottom. And you can see, even visually, you can see that the signals are the same. It's 1, 1, down, 1, up, down, 1, 1, 1. Okay, so there you go. You can actually see that the original signal has been recovered by the convolutional decoder, and that signal is now coming out of the decoder. We take the signal out of the decoder and we feed it up into the error counting modules, just as we have done in the previous experiment. So we pass it into the error counting modules and we compare the signal with a local, let me move this across, our local sequence generator, and we do the synchronization once again using the sliding window correlator. We take the error signal, and if I lower the webcam, you can see the down here you can see the errors accumulating because it's not synchronized, and as soon as I touch the probe, the sliding window correlator synchronizes the local generator. We have no more errors accumulating, and we're now in a position to do bit error rate measurements. So with that in mind, we can come back up to the scope. Looking at the scope, if we now increase the noise in the channel, This is the original data sequence, and here is the recovered data sequence. You can start to see errors are visually are visible. They're errors that the convolution decoder is not able to correct. And looking back down at the pulse counter itself, you can see also the pulse counter has got errors accumulating on it as well. And taking these measurements, as per the previous experiment, you plot the signal to noise versus bit error rate measurement curves, and the students are able to study the performance and develop a deep understanding of convolutional encoding using both systematic and non-systematic codes, which are selectable from the front switch, etc. And we have the signal at the receiver, the received signal, being viewed at the decision maker as an I pattern. And as you can see, there's quite a lot of band limiting and a significant amount of noise, and yet the system is synchronized, and yet we have 0 errors being accumulated at this point. So it's just interesting visually to see how the convolutional decoding is able to eliminate errors that are clearly occurring. And if we increase the persistence on this scope significantly, to say 5 seconds, even to, let's say, to 10 seconds, you can see the level of noise, and clearly there are signals moving across the center of the eye, and yet the convolutional decoding still gives us 0 errors. Now, if we reduce the persistence a little and increase the level of noise into the system beyond that threshold, okay, now you can see errors are beginning to accumulate, keeping in mind that our transmission rate is 2 kilobits per second. That's 2,000 bits per second. We're only accumulating tens of errors per second, and you can clearly see visually that the eye is closing up significantly, whereas even just backing off 2 dB of noise already allows the convolutional coding to take effect and eliminate the errors to a significant degree. So the setup of the DSP itself is discussed in the convolutional decoder user manual information. All the setups, all the requirements and the pinout of the module are there. And as well, the board itself ships with this comprehensive course written by Stephen Tretter, Communication System Design Using DSP Algorithms, which especially targets the 6713 DSK. So with the TIMS DSP, you have example programs, you have programs which implement convolutional decoding and trellis-Viterbi decoding as well, and as well you have the ability to do a number of exercises with the information supplied in this DSP course.